All right, so in this video, we're going to talk about volumes by cylindrical shells. In earlier videos, we talked about volumes by cross-section. This is just a different method, and a method that's used a lot of times when the cross-sectional area, that A of x, might not be available or very easy to deal with. And as you saw in the last section, many of the integrals can be pretty messy. And so this is just another technique to help us find that volume of revolution. And so what I'm going to start with is just a basic picture and try to make this build this up a little bit so you can see it better. But much like even the cross-section method, it's going to be difficult to see a lot of times, and so I would really encourage you to look in your text at some of the figures that they have, as well as continue to research this online just to get a better visual of what's happening. Once it clicks and once you see it, you'll see it, but until then it can be a little bit challenging. And so what I'm going to do to make this as easy as possible is just start with a really, really simple picture. So we're going to treat this guy right here, this blue line, as our actual curve. And I'm going to take this blue line now and I'm going to rotate it around the y-axis. Okay. Now again, I've chosen this vertical line so that it's going to be very easy to see that when I take this now around the y-axis, I'm going to get this cylinder looking thing. Looks something like that. And so by computing the volume of this, it's going to essentially be a volume of a cylinder, which is going to be our pi r squared h. Now, you got to remember what we're doing here. To compute this volume, what we're actually considering are the infinitely many concentric cylinders inside of here. There would just be a bunch of these things that we're then continuing to find the volume of, and then that integral is going to add all that stuff up. Okay. Now, when it comes to the actual formula that we're going to use, I'm actually going to take this volume of a cylinder up here, and I'm going to dr it. When you think about it, the height of these cylinders, even the green ones, aren't going to change, but the radius of the cylinders are going to change. The radius of this blue cylinder versus this one versus this one versus this one, those are all going to be different. So I'm taking the derivative with respect to the thing that's changing, the dr. So on the left, we have a dv dr, and on the right, since we're taking the derivative with respect to r, we've got a 2 pi r h. Now, I'll go ahead and move the dr to the other side, and then I'll go ahead and integrate both sides. That gets us our volume again. So our volume would be the integral of 2 pi rh dr. Now, this is a pretty loose interpretation, mostly because of the fact that I've come up with such a generic case like this. But it's essentially doing exactly what it is going to be doing for us in even the more specific cases. Now, the thing to remember is we're dealing with x's and y's, and traditionally we want to go ahead and write this now in terms of one of those variables. So for the case that I want to start with, let's go with x's. We'll go the integral a to b, 2 pi r of x, h of x, dx. Now, that's not to say we can't go with respect to y, and we will here in a little bit, but I want you to remember, anytime you're using cylindrical shells and you're going around a vertical axis, you're going to be with respect to x, okay? Now, that's different from the cross-section method, but if you're going around a vertical axis and you're going to be with respect to x in the actual integral, the radius here and the height here, that's where your top and bottom and left and right come into play. The radius, as you can probably imagine in something like this, is going to be the right minus the left. And the height, and again, as you can see in the picture, is likely to be the top minus the bottom. So we'll look at a bunch of different examples here, but this formula that I have drawn right here, this is going to be the setup now for going around a vertical axis. So I'm going to go ahead, I'm going to clear the screen, I'm going to get a couple examples up, and then we'll take a look to see how this works. Remember, guys, I understand it's very difficult to see, in particular when I'm not in the classroom, being able to point out things and take questions directly. But please do some additional research and looking at figures and looking at stuff online and in your text to better understand these concentric cylinders in here, and how this formula really is just going to be adding up all of the infinitely many volumes of the cylinders. Okay, so you can see the example I have up on the screen here. We're going to be finding the volume of the region bounded by y equals x, the semicircle, and x equals 0, which is the y-axis. We're going to find the volume of it going around the y-axis, x equals 7 and x equals -8. You'll note that all three of these are vertical axes, and so these are all going to be dx type problems. Okay, so I'll start with drawing the region. And so the region that we're talking about, based upon the information that's given, would be this guy right here. We've got our semicircle, we've got our line y equals x, and then we're also bounded by the y-axis. And so really what we want is this guy right here. Okay, so I'm taking that now around the y-axis. So as I take that around the y-axis, what I'll do is I'll go ahead and put in here a vertical line. Remember, as I take this around the y-axis, that vertical line from here to the axis of rotation is going to be my radius. Even if I put the vertical line here, that would still be my radius, because we're coming up with these concentric cylinders inside of this solid. So being the radius, I'm going to call this guy from here over to my line, I'm going to call that x, okay? Because that's definitely something that's going to change based upon the cylinder. Now, the other benefit of having this vertical line in here like I have is not only going to help us represent that radius I talked about, but it's also going to help us with the top and the bottom. So as I go ahead and get this thing set up now, I'm going to have the integral. I'm going to have my 2 pi. My radius now, my radius is going to be the x minus the 0. So that's going to be that right minus left I talked about. So this guy would be our x minus the 0 for where our axis of rotation is. So we've got our x minus 0. And then for the height, that's going to be the top minus the bottom. The top part would be the top part of the semicircle. The bottom would be then the actual line. So we've got our root 4 minus x squared minus the x dx. Okay, so this is our right minus left, top minus bottom. In other words, this is going to be our radius, and this is going to be our height, based upon how I had this laid out in the last one. And so there's our setup so far. The only other thing that we're missing now would be the bounds from here to here. I'm not going to necessarily show that. You can certainly take these two things off your own, set them equal to one another and solve them, and you would see that you come up with a 0 and a root 2 for those. So that would be our setup there. Okay, so now we'll go ahead and move down to the next one, where we go around x equals 7. And so for x equals 7, again, our picture is going to be the same, where now we have this shape here, and we're going around x equals 7, which is over here. Since, once again, we're going around a vertical axis, I'm going to sketch in this vertical line, which is going to help me with the radius being my x, and then it's also going to help me with the top and the bottom. Now, you'll see here very quickly that there's not much different in this problem and the last problem. We're still going to be on the interval 0 to 2. We're still going to have our 2 pi. Our radius is going to change, but our height is not, right? The top and the bottom is not going to change. So that's going to be a 4 minus x squared minus x dx. But now we need to figure out that radius. So the radius, remember, it's going around this direction. We're going around this way right here. So the radius that we're constructing is actually going to be this guy right there in red. So what is that that I have in red? Well, that's going to be your distance of 7 from here to here. So 7 from here to here minus this part right here. So minus the x. So that radius then would be our 7 minus x in this case. All right, moving on to part C. I kind of like doing these one after the other because the first example was probably a little bit hard for you to understand, but now as we kind of get into these next few, it's hopefully a little bit easier and starting to make more sense. So here's our shape, here's our region R. We're going around now, x equals -8. We're going to put that vertical line in there, which is going to represent our x value. It's also going to represent our height. So setting this one up, you'll see it's the same way. We're still in the same interval, 0 to 2. We have our 2 pi. Our radius is going to change, but our height is not. And then that radius, as we now go all the way around this way, is going to be represented by this red line right here. And that guy is actually going to be an x plus an additional 8 units. So that red line is going to be an x plus 8 units. So we'll have this x plus 8 in here. And so those are the setups now, as you can see, going around vertical axes. The cross-section method is the one that's taught first and is probably the easiest one to see. But once you see this, I really think, once you understand what you're actually visualizing and doing, most people like to set up these types of problems more because there's an additional component that you don't have to take into consideration in the other one.